So today we're going to look at what's called improper integrals. And before we go into that, I want to take a look at what if we want to find the area between the x-axis and the curve for this function y equals e to the negative x over 2. And let's say we want to stop this right here at this point right here. And we'll call that b. So we're going to end our integral at b. So we're going to call this function that generates the area a of b. And that's going to equal the integral from 0, because this one's starting at 0, and we're going to end it at b. And it's the function e to the negative x over 2. And then dx. And if you did the antiderivative of this, you would wind up with negative 2e to the negative x over 2. And then we want to evaluate this from 0 to b. Okay, and so we can use this to, like, okay, we want to stop this integral wherever we want to, and let's call it b, right? Okay, so that means if we evaluate this, a of b becomes, and we put b in, so that'd be negative 2e to the negative b over 2, and then minus, and then we put 0 in, so that would be minus, and then negative 2e to the negative 0 over 2. Which really doesn't make sense, right? That'd just be 0. Okay, and then this would be e to the 0, and e to the 0 is 1, so this is negative 2, and we're subtracting. So this actually becomes plus 2. So my function that generates the area a of b would be negative 2 e to the negative b over 2, and then plus 2. All right, so we can use this. If we come up with a function where we stop the integral, we can actually use that same function if we make this go forever. In other words, what if we have a function that there is no stop to it, like this function actually goes to infinity? So what we can do is this, and this is the whole idea about evaluating improper integrals. We can change this to a limit, and what we would do is we'd make this b go to infinity. So we'd want to find the limit as b approaches infinity of a of b. And so that would give me the area with my upper limit going all the way to infinity. Okay, so this would equal the limit as b goes to infinity of what my a of b function is. And right here's my a of b function. Now we have a negative exponent here, right? So this really becomes negative 2 over e to the positive b over 2 power, and then plus 2. And what happens when b goes to infinity? Okay, so b in this exponent, b is going to get really, really big, which is going to cause this fraction to get really, really big, which means e to a really big positive number is going to be really big. So this denominator is going to be really, really big. Well, if the denominator is really, really big, that's going to make the overall fraction here get closer and closer to 0. So again, let me go through that again. Okay, so this, because there's a lot of chain of like logic going on there. Okay, so as b gets really, really big, right, we're dividing by 2. This exponent is going to be really, really big, and e to a big number is going to be a really big number, and then we're going to take negative 2 and divide by a really big number, which means it's going to get closer and closer to 0. So this is really going to be 0 plus 2, or 2. So the limit as b goes to infinity of this function, this integral function, is 2, which means if I ask you to find what's the integral from 0 to infinity of e to the negative x over 2 power dx, we could rewrite that as the limit as b goes to infinity of the integral from 0 to b e to the negative x over 2 dx. And this integral ending in that b creates this integral function that we talked about earlier. Okay, so this is how we're going to evaluate them. All right, if the upper limit is infinity, then we're going to go from some number to b, wherever we want to start this. Wherever this one starts, this one's going to start. So let me scroll up a little bit. Let me slide the paper up, and then we'll talk about, okay, so you can do this with going to negative infinity also, and we can also do it from going from negative infinity to positive infinity. And so let me show you how to do that next. So here's the three different situations we can have. Okay, so if I ask you to go from a to infinity, that's actually the one we just talked about. So if we want to go from some number a to infinity of f of x, we can just find the limit as b, and we call the infinity b here. B go to infinity from a to b of, and evaluate this integral f of x dx. If fx continues on negative infinity to b, all right, so, and we ask you for what's the integral from negative infinity to b, then we're going to find the limit as a goes to negative infinity. So this is what we're going to call a, and we're going to go from a to b of f of x dx and evaluate this and find the limit as a goes to negative infinity. And sometimes these will come out to be values and sometimes they won't, all right? And so we say it either diverges or converges. And then if we want to go from negative infinity to positive infinity, then we have to break this up. So we're going to have to go from negative infinity to some c, and then from c to infinity. We're going to have to break it up like this. And then we're going to take the limit as a goes to negative infinity for this one, plus the limit as b goes to infinity on this one. So c is just going to be some number in between a and b. And you can think of like a and b as being your left and right endpoints. Okay. And c has to be some, it can be any real number. Okay. All right, let's start doing some problems and just go over different situations that you can come across in these improper integrals. So for this first example, we want to evaluate the integral from negative infinity to infinity of e to the x dx, or state that it diverges. So if we actually get a number value out of this, then we're gonna say it converges. Okay, and we can evaluate it. If we get infinity or negative infinity, that's not a value. Okay, and so we would say it diverges. All right, so right off the get-go, what we want to do is break this up. So we're going to go from negative infinity to positive infinity of e to the x dx. And the way we can break this up is and 0 is somewhere in between here. It wouldn't have to be 0. 0 is just a nice one to work with. We're going to integrate from negative infinity to 0 e to the x dx. And then we're going to add to that the integral from 0 to infinity of e to the x dx. And so this is our a, and this is going to be our b. So for this first one, we're going to take the limit as a approaches negative infinity, and we're going to integrate a to 0 of e to the x dx. And then we're going to add to that the limit as b approaches positive infinity of 0 to b e to the x dx. And I picked one just to start out with, like that we could really integrate really easily, okay? So this becomes the limit as a approaches negative infinity, and the integral of e to the x is just e to the x. So we're going to go e to the x, and we're going to evaluate this from a to 0, and then plus, and this will be the limit as b goes to infinity of, again, the antiderivative is the same, e to the x, and we're going to evaluate this from 0 to b. Okay, so then this is the limit as a approaches negative infinity, and this becomes e to the 0 minus e to the a, and then plus the limit as b goes to infinity of e to the b minus e to the 0. And recall that e to the 0, so e to the 0 power is actually going to be 1. So this is the limit as a approaches negative infinity of 1 minus e to the a plus the limit as b goes to infinity of e to the b minus 1. Okay, so if we evaluate this as a goes to negative infinity, so we got to think of that as being a really big negative number. Well, that's going to be an exponent. So this is going to be 1 over e to the positive number, right? So the denominator is going to get really, really big. So this is going to get closer and closer to 0. So the limit of this would be 1 minus 0. So this is equal to 1 minus 0 plus Okay, as b goes to infinity, this is going to be e to a really big number. Well, that's just going to cause e to a really big number it's going to be a really, really big number minus 1. So we can think of this as being infinity minus 1, because when we evaluate that limit would come out to be infinity. And so what we have here is 1 minus 0 plus infinity minus 1, and we have 1 minus 1, that'd be 0 minus 0, so we just have infinity here. Okay, so what does that mean? That means the integral doesn't exist. Like, you cannot integrate from negative infinity to positive infinity of e to the x dx. It doesn't exist. The actual area, okay, is infinity. It's infinite area. So what that means in turn, let me slide my paper up a little bit, is that we would say the integral from negative infinity to infinity of e to the x dx diverges. So it doesn't converge to one number value, right? All right, so that's considered a simple one, all right, even though it took almost a whole page. All right, so now let's take a look at, and we still have all of our techniques for integration. Integration by substitution, integration by parts, partial fraction, decomposition. We have all of those things, okay? So let's look at the next example. So for this one, we want to evaluate the integral from 1 to infinity of dx over the square root of x. So I would rewrite this as x to a power. And so the square root means we're going to have 1/2 power. And since it's the denominator, we're going to have a negative 1/2 power. So that means we're going to find the integral from 1 to infinity of dx over the square root of x and that square root of x. And that would equal the integral from 1 to infinity of x to the negative 1/2 power dx. And so we need to make that become a limit. So, and that, since that's the upper limit, I'm going to call this b. So we want to look at, okay, so what's the limit as b approaches infinity of the integral from 1 to b of x to the negative 1/2 dx. And now we can integrate this, right? So this becomes the limit as b approaches infinity, and we would add 1 to our power. So adding 2 halves to this gives me x to the 1/2, divide by 1/2, or multiply by the reciprocal of that, which is multiplied by 2. And so that's our antiderivative. And then we're going to evaluate this from 1 to b. So that means this is equal to the limit as b approaches infinity of, and x to the 1/2 is really the square root of x. So this is 2 square roots of x evaluated from 1 to b. So once again, this is the limit as b approaches infinity. We have to keep writing the limit until we evaluate it. And so this would be 2 square roots of b minus 2 square roots of 1. And so the square root of 1 is 1. So this really becomes the limit as b approaches infinity of 2 square roots of b and then minus 1. And so if b goes to infinity, well, the square root function, as the input here gets bigger and bigger and bigger, the square root function gets bigger and bigger and bigger, right? And this minus 1 is really insignificant. So that means this is going to go to infinity also, which means this integral diverges. So now we can say, and let me slide my paper up just slightly. Okay, so now what we can say is the integral from 1 to infinity of dx over the square root of x diverges. All right, let's look at another one. So here's one that we're looking at. Okay, so how do you evaluate the integral from -1 to infinity of dx over x squared plus 5x plus 6? And if you look, the degree of this polynomial in the denominator is larger than the degree in the polynomial in the numerator, right? So that's a kind of a hint, like, okay, we need to look at partial fraction decomposition. When this power is bigger than this one, we need to look at partial fraction, okay? So I'm not gonna, because in an earlier video, I went over how to do partial fraction decomposition, but if you were to do it, all right, 1 over x squared plus 5x plus 6 becomes 1 over x plus 2 minus 1 over x plus 3. So this, if we were to get a common denominator and combine them, we would wind up with this, okay? And what we use there is partial fraction decomposition. So I'm just telling you what I did to get this. I'm just not showing the work. Okay, so we want to evaluate this. So this function is going to become this function. So we're going to start out with the integral from -1 to infinity of 1 over x squared plus 5x plus 6 dx. And that becomes equal to the integral of 1 over x plus 2 from -1 to infinity dx. That's just that piece, right? And then minus the integral from -1 to infinity of 1 over x plus 3 dx. Okay, since this is going to infinity, we're going to call this b and this b. And so we're going to find the limit as b goes to infinity, and our integral becomes -1 to b 1 over x plus 2 dx minus the limit as b approaches infinity of -1 to b 1 over x plus 3 dx. Okay, so you could use integration by substitution. Okay, so I'm kind of cutting some stuff out, like, okay, why is it this? I'll tell you why, all right? But if you did like integration by substitution, let this be u, all right, then we would wind up with the limit as b approaches infinity of, and this would be the natural log of the absolute value of x plus 2. And we need to evaluate that from -1 to b, and then minus the limit as b goes to infinity of, and same thing, all right, this would be also the natural log of the absolute value of x plus 3. And we're going to evaluate this one from -1 to b. Be careful, because I just realized like my negative just came, I lost my negative right there with my integral symbol. So that should be a -1. All right, so now, okay, we're going to put b in. So that would be the limit as b approaches infinity of the natural log of the absolute value of b plus 2 minus the natural log of the absolute value. If we put -1 in here, that would be the natural log of the absolute value of 1. And then minus the limit as b approaches infinity of, and putting b in here, that'd be the natural log of the absolute value of b plus 3. And then minus the natural log of, if we put -1 in, that'd be the natural log of the absolute value of 2. And so natural log of 1 is really, we can rewrite this as e to the 0. So this just becomes, or the natural log of e to the 0. So this is just be 0. So this becomes the limit as b goes to infinity of the natural log of the absolute value of b plus 2. And I'm going to write this as just, because they're the same limit, so we can pull it out, and then minus ln of the absolute value of b plus 3. And then minus, we really don't need the absolute value because 2 is already positive. So we could rewrite this as just ln of 2. And I'm sorry, made a mistake there. When we pull this out, we got to subtract this one, right? But because we're subtracting here and we got to distribute, this is going to actually become plus. So plus ln of 2. And we're going to evaluate that as b goes to infinity. Now, how do you evaluate this? Well, we got to use some logarithm properties. So remember, a logarithm property says if you take the log or any logarithm of something minus log of something else, you can write that as a quotient. So this becomes the limit as b approaches infinity of the natural log of, and it'd be the absolute value of b plus 2 over the absolute value of b plus 3, and then plus ln of 2. So what does that mean? Okay, so as b goes to infinity, this plus 2 and this plus 3 is really insignificant for really big values of b. So really, this numerator and this denominator, they're only one away from each other, right? So they're really close to being the same thing, especially when b is really, really, really big, right? So Matthew Compass. Okay, so back to this, because the bell rang. All right, right here, what we were saying is, okay, this plus 2 is insignificant, the plus 3 is insignificant. So really we have the absolute value of b over the absolute value of b. Well, that's just 1. That's the natural log of 1, right? So when we go to do this, right, this really becomes ln of 1 plus ln of 2. Okay, because as b goes to infinity, these get closer and closer to being really the ratio of them gets closer and closer to being 1. Okay, now what is 1? Remember, this is base e, so we could rewrite this, and I said this earlier up here. We could rewrite this as e to the 0, because e to the 0 is 1, plus the natural log of 2, and e to the 0. Let me slide this up a little bit. E to the 0, right? The natural log of e to the 0 is just 0. So this is 0 plus ln of 2, or ln of 2. Okay, so when we go, that means this converges. That's our answer to this. So that means this integral from -1 to infinity of 1 over x squared plus 5x plus 6 dx is equivalent to ln of 2. There, and let me slide it up, sorry. So again, like I said, the integral from -1 to infinity of 1 over x squared plus 5x plus 6 dx is equivalent to ln of 2. So for this next one, we want to evaluate the integral from 0 to infinity of x plus 1 e to the -x dx, or state that it diverges, right? So once again, we're going to go integral from 0 to infinity of x plus 1 e to the -x dx is equal to, so we're going to replace this infinity with a b. So we're going to make the limit as b goes to infinity, the integral from 0 to b of x plus 1 e to the -x dx. Now, if you look at this, we have a product, right? We have x plus 1 times this. And then we also realize that, okay, this isn't really integration by substitution, because if I try to like let u be -x, then du would be -1, and we wouldn't be able to pick up this x plus 1, right? And so we got to realize that this is integration by parts. That's also where we can integrate a product like this, okay? And this is a polynomial, and this is an exponential. And so what we remember, lipid, that's the choice of what we want u to be, right? Okay, so if we do this, we're going to let u equal x plus 1, and we're going to let dv, and then we want that lipid is what you choose for u. Okay, logarithm, inverse functions, or inverse trig functions, polynomials. I can't spell lipid. So logarithms, inverse trig functions, polynomials, exponentials, and then trig functions. Okay, so dv, all right, we're going to want to, since we don't have a logarithm and we don't have an inverse trig function, the first thing we have is polynomials. Okay, and so dv is going to be the other factor here, e to the -x, and then dx, and then du is going to be the derivative of this. So that would be dx. And v is the integral of this, right? So that would be negative e to the negative x. Now it's ultraviolet voodoo, right? If you remember me saying that. So this is equal to the limit. It's just a way to remember how to write it. Okay. B goes to infinity of ultraviolet. So U times V. So that'd be x plus 1 times negative e to the negative x minus the integral. And here's where we pick up the integral from 0 to b. And voodoo, right? So that's v du. So that'd be negative e to the negative x dx. Okay. So then what can we do next? Well, this negative can come out in front. So this is equivalent to the limit as b approaches infinity of negative and then x plus 1 e to the negative x. This minus we can pull out of the integral. So it becomes plus the integral from 0 to b e to the negative x dx. Okay, and we could do an integration by substitution right here, okay? Or you could just realize, oh, this is just going to wind up being negative e to the negative x when you take the antiderivative of it, okay? So this is equal to the limit as b goes to infinity of, and we got to evaluate this whole thing, okay? And so I have negative of x plus 1. Let me hold off on that. What my thought. And we're going to integrate this one. So that would be plus negative e to the negative x. And we're going to evaluate this from 0 to b. But we also have to evaluate this one from 0 to b. So I'm going to put another bracket around this, because we have to evaluate both of them, if you remember this, okay? And then I'm going to close my outer bracket here. And so this becomes the limit as b approaches infinity. If we put b in here, this would be negative b plus 1 e to the negative b. And then we're going to minus, but we're going to minus a negative, right? Because this is going to be negative. So that's actually going to become plus. And if we put 0 in here, it'd be 1 e to the negative 0, or e to the 0 power. And that's evaluating from 0 to b, this piece of it. This piece of it would be plus, and then we put b in, so that'd be negative e to the negative b. So plus negative e to the negative b minus negative e to the negative 0, or just 0. Okay, so let's clean this up a little bit. So this, because we still haven't done the limit. So the limit as b approaches infinity. This is going to be negative b plus 1 over e to the b. E to the 0 is 1, so this is going to be 1 times 1, so that's just plus 1. And this one's going to be minus 1 over e to the b. And this is going to be plus, and e to the 0 is 1, so plus 1. So as b goes to infinity, okay, the denominator is going to be growing, but it's not going to be growing that much. E to the b, this is going to be growing way, way more, right? We're faster because it's an exponential. So this is going to get really, really big compared to this one. And so this whole thing is going to go to 0. So this is going to wind up being 0 plus 1 minus, and this is also going to go to become a really, really big denominator, which causes 1 over a really big number to be close to 0. So minus 0 and then plus 1. So 0 plus 1 minus 0 plus 1. Well, that'd be 1 plus 1. So it'd be 2. And that's what the answer is to this. So if you integrate, and that means this converges, okay? So that means the integral from 0 to infinity of this function x plus 1 e to the negative x dx is simply equal to 2. Kind of crazy how sometimes they'll converge and you'll get an answer out of it, and then sometimes they don't. All right. And so here for our last problem that we want to do is, let's evaluate the integral from negative infinity to infinity of dx over 1 plus x squared. So because it's going from negative infinity to infinity, I'm gonna have to break this up into 2 integrals, and then I'm gonna have to take 2 different limits. Okay. All right. So here we go. So negative infinity to infinity of 1 over 1 plus x squared dx is equal to the integral from negative infinity to 0 of 1 over 1 plus x squared dx, and then plus, and then we're going to take the integral from 0 to infinity of 1 over 1 plus x squared dx. And so this is going to be our a, and we're going to let a approach negative infinity. So the limit as a approaches negative infinity of the integral from a to 0 of 1 over 1 plus x squared dx plus the limit, and this is going to become our b, so b approaches infinity, of the integral from 0 to b of 1 over 1 plus x squared dx. Okay, so we got to recognize this as being the derivative of tan inverse of x. So the integral of 1 over 1 plus x squared, that's just tan inverse, because the derivative of tan inverse is 1 over 1 plus x squared. So this is equal to the limit as a approaches negative infinity of tan inverse of x evaluated from a to 0, and then plus the limit as b approaches infinity of, this is also tan inverse of x, and this is going to be evaluated from 0 to b. Okay, so that makes this equal to the limit as a goes to negative infinity of tan inverse of 0 minus tan inverse of a, and then plus, and hold on, I forgot to write my limit statement. And then plus the limit as b approaches infinity of tan inverse of b minus tan inverse of 0. Okay, so now the tricky part. Okay, so we have to recall, okay, for me, I think about the graph of this to evaluate this. Okay, so we know that y equals tan x. We should know the graph of y equals tan x. Okay, and it has a vertical asymptote at x equals negative pi over 2, and another vertical asymptote at x equals pi over 2. And the graph of tan inverse looks something like this. So it's going from negative negative quadrant to positive positive quadrant, right? So when you do the inverse of this, y equals tan inverse of x, these vertical asymptotes are going to become positive, or not positive, horizontal asymptotes. So now what's going to happen is we're going to have a horizontal asymptote at negative pi over 2, and also at y equals pi over 2. And again, this is going to go to the positive quadrant. So it's going to come right here, right? And it's going to come through 0, and it's going to end up right here. So that's going to actually help me evaluate a lot of these. It's going through the origin. I didn't draw it very good. So it's going to go through 0, 0. So right there is 0, 0, because tan goes through 0, 0. Okay. But look, as it gets really, really, as your x gets really, really big, this is getting closer, closer to pi over 2. And as x goes to negative infinity, it's going to go to negative pi over 2. So that's going to help us and evaluate it at 0 too. So right here, because it's going through the origin, the tan inverse of 0 is going to be 0. So this becomes the limit as a approaches negative infinity of 0 minus tan inverse of a. So that would just be negative tan inverse of a. And then plus the limit as b approaches infinity. And again, this is 0. So okay, I'm sorry, this one's 0. Sorry. And then tan, sorry. So this is going to become the limit as b approaches infinity of tan inverse of b. And this one is going to become 0. So we really don't need it. And so as a goes to negative infinity, so as this goes to negative infinity, right, this is going to get closer and closer and closer. This is going to get closer and closer to negative pi over 2. Tan inverse of a is going to get closer and closer to negative pi over 2. But we have a negative out here. So that means we're going to have negative of negative pi over 2. And then plus what happens when b goes to infinity. When this goes to infinity, our graph is going to go up and approach pi over 2. So this is going to be plus pi over 2. So we have pi over 2 plus pi over 2, which is 2 pi over 2, which is pi. So this integral is pi. Okay, so that means if we take the integral from negative infinity to positive infinity of 1 over 1 plus x squared dx, we know that this integral is going to come out to be pi. And whenever it comes out to be a real number, then it converges. Okay, so that's how you do these problems. Okay, these improper integrals, you actually switch them and make them become a limit, and you make one of your limits either your lower limit or your upper limit, or both if you're integrating from negative infinity to positive infinity. You're going to break it up into 2 integrals then. All right, that's how you do these. All right, see you next time, guys.